So now let's discuss, okay, so now let's discuss hardness and hardness testing. Number one, hardness is the ability of a metal to resist penetration or indentation, right? And that's pretty easy because once you think about a hardness tester, once you see what one looks like, which we have in our shop, there's an indentation ball, and then we have to measure the indentation. So its ability to resist indentation. There's three basic groups of indentation hardness tests should be discussed: Burnell, Rockwell, and micro hardness. In general, three different types differ from one another in the size and indentation produced. Burnell is the largest and micro hardness is the smallest. Naturally, Burnells, you're going to get a broader surface. So Burnell is usually used on larger grain materials. So that would be like lead, brass, things like that. You're gonna, and also softer. You can use just a home Burnell tester. And basically, what you do is you're going to push it in. You're going to indent it. We'll get to it here in a second, but with all of them, right? So you put a certain amount of pressure on there, okay? You bring it down to it, and in the Rockwell one, there's a major and a minor load, but either way, the overall general conception is this. You're going to bring it down, you're going to put so much force on it. Let's just say it's 100% of the force, or 50 pounds for everything we do, and then when we're done, we're going to pull it up, and we're going to measure the difference from right there to right there, okay? Sorry, I'm trying to get this here. We're going to measure the difference from that edge right there to that edge right there, and it's going to be a round surface, or in some cases maybe a diamond. But that's the number we get, and then we come over here and we look at the indentation diameter. So it ended up being 2.45 millimeters, and that's going to correspond to, well, what was the load? Was it 500 kilograms, 1,500 kilograms, or 3,000, depending on the material? Then we can start to see, oh, okay, so that's what's telling me what's my Burnell hardness. Nice, okay. Making sense now? All right, so I want you to read through this. Basically, the big things I'm going to talk to: diameter of the impression, reading the hardness value from a table. It tells you that one there here in a second. And then it does talk a little bit about, the difference between, there's Burnell. Let's see, where's my Rockwell? Here it is. Next type of hardness discusses the Rockwell. This type encompasses numerous variations of the same basic principle, but uses indenters of several shapes, sizes, and diameters. The indenters used are the diamond braille, shown in figure 611, and 1/16, 1/8, quarter, and ½ inch in diameter, hardened steel balls. Smaller indentations in Burnell testing permits localized testing of a relatively small metal area. This is really important because of the grain structure. We go back to that cold working thing just a second ago. We want to look at the overall hardness of this material alone. We can just bring it in here and we'll cover 2 or 3 grains maybe, or say my thumb, and I'm going to get a broader aspect of 10 grains, okay? But now if I want to come over here, and naturally if I want to say a lot smaller tester, I can get here to where I'm just testing 1 grain, right? And then I get into the more micro hardness, Vickers and Knoop and so forth, and I can come in and actually get right on the grain boundary and see how far I can penetrate into there, okay? So that's the difference between macro to micro hardnessing, or hardness testing as well. Talk Rockwell there. Okay, so no matter which Rockwell scale is being used, basic steps are essentially the same. You prepare the surface, place test object, apply a minor load, okay? Then you apply the major load, then you release the major load, you read the dial, then you release the minor load and remove the part. So basically one of the things to remember is if it's talking about 2 loads, you're dealing with a Rockwell tester, okay? So here's the difference. Burnell, 10 millimeter sphere of steel or tungsten carbide, right? Vickers, which is a diamond pyramid. A Knoop, which is a diamond pyramid as well, but if you notice, a lot finer point, right? And we can also get down in there to where we'd be able to get into that grain boundary here and be able to touch on it. Here's the Rockwell type. So there's a diamond cone, or there's a sphere, 2 different multiple sizes of spheres. And then you can also look at the angle of approach, the shapes of indentations and so forth as well, okay? Micro hardness, I want you to read through this sections are here. High magnification is required. So there are 2 major types of micro hardness tests. Vickers and Knoop both use diamond indenters, but their configurations are slightly different. It talks into here. So, I mean, it's amazing when you look into this. that we can get down almost to an individual grain to measure the hardness testing of it. So particularly for some of these folks around here that are doing like titanium or something, it's really important for government contracts to be able to see this. So here kind of walks through steps involved in the Rockwell hardness. Okay, read through those. Here's your Burnell, here's your Rockwell, whether it be C or B, Vickers and Nuke, and then across here it'll give you a tensile strength in 100,000 psi. Okay. All right. Okay, so let's see what we can do for toughness. Okay, making sure I'm not missing anything here. All right, so toughness. Next mechanical property to be discussed is toughness. In general, toughness, the ability of a material to absorb energy. We talked about that with the boxer, right? Metal having higher values for stress and strain is considered to be tougher than a metal with low values. And this goes back to being able to withstand that impact. Particularly, I always talk about the rock crusher, right? Another common term is notch toughness. This differs from toughness and it refers to the metal's energy absorbing ability when there are surface flaws present. Okay? And then we get down in here, we talk about notch toughness further differs from toughness, and that toughness usually defines a material's behavior when loaded slowly, while notch toughness values reflect the energy absorption, which occurs at a high rate of loading. It's impact strength, okay, is the big thing. This is the difference between, a lot of times you're going to hear this notch toughness is impact strength, braking energy, okay? So the best way I can describe this, in all honesty, is to think of a 2x4, okay? And if I take a 2x4 and I've got a notch on one side of that 2x4, so say it's like this, but this is a 2x4 and there's a notch there, okay? And I think about a kid, say for example, my 9-year-old son at this point's at 95 pounds or 100 pounds, and if he jumps on that, it's gonna break much easier due to that notch than it would if that notch was not there. If that notch if it was just like this, it might actually bend and just absorb and be elastic. Well, it might grow some, but it probably wouldn't shear and break. But this is a good example of impact strength and notch toughness. If this notch is there and I jump on that 2x4 from this direction, all of a sudden that crack, number one, because it's there and it's reduced section, but also because of its position here at the end. So this is a very sharp indentation of a crack. So we talk about crack tip displacement. This is where it can be valuable to where it's easier. A crack will start from a diamond than it would from a round surface anytime. Here it doesn't have a real sharp edge to go off of, but right in here it's got a sharp edge to grow from, okay? So that's one of the best ways I can explain notch toughness is think about that 2x4. If we put a notch on one side of it and we jump on it, it's easy to break, right? Back when I was a kid and I was in martial arts, I used to think that was the coolest thing. I could cut one side of it and then I was actually able to break the wood. Otherwise, I just hurt my hand. That was no fun. All right. In general, a metal's notch toughness decreases as its hardness increases and its temperature is reduced. Again, temperature has an effect on everything. So we talk a little bit here. Performing tests determine notch toughness of a metal. Usually tries to determine the temperature at which the fracture behaviors change from ductile to brittle. This temperature is referred to as the metal's ductile to brittle transformation temperature. Right here is your Sharpie V-notch specimen, which we talked about earlier. So there's an actual, exactly a notch machined in this at a certain position, right? You can read through this section here. Read through here. Sharpie V-notch are done in sets of 3s to get a good average overall. And they're done at different temperatures. And the way that best way I can show you different temperatures is so I'm going to jump over here to chapter 8 a little bit, which is why chapter 6 and 8 are kind of in the same area as well. All right. So, no, it's not in here. So let's look at our slide. Talk about hardness testers, toughness. So here's a Sharpie V-notch machine, real quick. this specimen's got its 100-pound axe, right, so to say, and it just falls down every time. Same weight, same consistency for materials makes it very important. So right here, here's a good example of one, and this PowerPoint's kind of rough. But if you look on the far right, that's at a 40 degrees above zero temperature, right? And if you look, as you go to the left, as our temperature drops, we become a lot more rigid, okay? So what's the surface condition? Again, most of you folks have heard me talk about running a Caterpillar in South Texas or South America, maybe, on certain parts of it where it's really hot. It's going to be much different than plowing a field in Montana or Wyoming or the Colorado Rockies where everything's at 8,000-9,000 feet. You know, you're going to see 40 to 60 below where things get very brittle at that point. But in Texas, we're not going to see that type of temperature, so our metallurgy needs to change. And this is one of our biggest problems with people that travel the country and work shutdowns. And it's a big challenge for inspectors to be aware of this as well, because as you move around, you need to understand that maybe this machine was built. For example, the mine that I worked at, Bucyrus area, used to build drag lines for cold weather drag lines versus hot weather drag lines. So between Texas and Wyoming or Montana, they'd be two completely different setups as far as mast and metallurgy. Okay. All right, read through this section here. Transition temperatures. Talk about fatigue strength. Strength necessary to resist failure under repeated load. You know, basically I've got a few notes here just to kind of help me think of some things that I would talk about at this point. Here's also a transition temperature. Shows you kind of just what we talked about, right? So you've got the cleavage fracture or the tears, so to say, versus a shear in there. And then you can see the difference between the temperatures as well. So here's the percentage, but then higher elevation goes up, so forth, okay? And they want to do this every, you go look at the box of welding rod and it tells you basically what its temperature rating and stuff is for, and they've done that. Everything's got to match a Sharpie V-notch. It's so much temperature and so much force. Okay. So, notch toughness. Now we start to look at just being general roughness alone, right? So here's a pretty rough looking weld. So when we want that nice smooth looking weld, even if it's above face reinforcement, a smoother weld means less notch toughness and less problems that can evaluate or propagate from that area. So here we talk about discontinuity such as undercut, overlap, excessive reinforcement, and basically just overall surface roughness. I've seen rough welds that just looked horrible, and I've called them on that before even. General rough welds, they need to be fixed, cleaned up, in better positions. So here's the other thing that's pretty cool. Look at this. While fatigue failures can result from internal weld discontinuities, those on the surface represent a more significant concern. And here it goes to talk about this. So everybody's like, oh, well, it looks okay here, but we need to see what's on the inside. Remember, there's a lot of things that start from the outside, and I want you to go back to think of that 2x4. You can put a hole in the middle of a 2x4 and it can absorb a lot more energy than if you were to do a notch on the edge of it, okay? Soundness testing. Basically every nick, break, fillet weld, every test we do from a destructive test is to test soundness, okay? And then non-destructive, we check it with radiography, ultrasound, whatever we need to in there as well, okay? Transverse weld bend specimens, 3 basic types: guided bend, roller, quip guided bend, and wraparound. So we have a guided bend, okay? Here's the jig that we had on the old one. I don't remember if our new one has rollers on it or if they're just a set of shoulders just like that, okay? 3/8 inch specimen, we've been around 1.5 inch diameter mandible, results in 20% elongation of the outer surface. All right. Here's a much larger one. You put it in here and it wraps it around it. It's the same thing. It's just a little bit different way of going about that. Okay. Longitudinal bend specimen. So the nick break test. The nick break test is only just used in API 1104. And here's a good example of a nick break test. We'll take a weld, and we basically just want to come down right below it, right? Basically to the actual weld itself. You never do the root, okay? You only do the face. And then what you do is you cut those in just a little bit according to that spec, right? You got a 1-inch coupon, 3/4 of an inch in, so you're only coming in 1/8 of an inch on each side. But you're trying to force it to break in the middle of that weld, and then you pull it apart, and you want to make sure that there's no indications in it whatsoever, okay? And again, nick break is only used and recognized in 1104. So now we start into some alloy groups. That's the biggest thing right here. The amount of carbon present has the greatest effect on the metal properties. Read through this section. And stainless steels contain at least 12% chromium is the way that it's still reading. Now we know with some of the new metallurgy that we're seeing that that's not always true. Okay, but go ahead and read through this. Here's your designations. Tells you some of your major alloying groups. Okay, so chrome moly, you know, here's straight moly. Chrome moly is 41. Nickel chrome moly 43. You know, there's a lot of them that are in here that are very close, very similar, but for different, we want different things for different reasons within that alloy. All right, which are the five major groups of stainless steel are austenitic, martensitic, ferritic, precipitation hardening, and duplex grades. I want you to read through all these: carbon, sulfur, phosphorus. It wouldn't hurt for you to understand or write those down, kind of telling you the difference before. All right, so basically I want you to look at this. You'll hear some old timers talk a lot of times when you talk about different grades of steel. You can say 15.5, so it's 15% chromium and 5% nickel. 17.4, 18.2. They have different tensile strength, different amounts in them, and they're used for different things. So you can also look at this like an 18, you know. Look at this amount of chromium within that. So for corrosion resistance, but then also for lower temperature elevations possibly. You get up here into 310, 316. That's why 316 is used a lot of times versus 304. Okay. Silicon, only usually, but it's used as a deoxidizer. Think about your MIG wire, right? Second most important is manganese. It prevents the formation of iron sulfide inclusions. Nickel. Nickel is frequently used to improve a steel's toughness at low temperatures and to improve its corrosion resistance. Okay. Now, come back up here real quick. Niobium and dissolved gases, hydrogen, oxygen, and nitrogen. Okay. Alloying groups, there's aluminum. Read through this section. Nickel alloys. We get down here, we start talking about, you know, many of the high temperature alloys and corrosion resistance have nickel percentages to the 60 to 75% range. These would include several property alloys such as proprietary alloys such as Monel and Inconel and Hastelloy. So these would be used in like steam generators and stuff like that, power plants, where they're always at a high elevated temperature, and for certain fertilizer factories as well, right? So the product that they're pumping around has to stay at 300 to 400 degrees at all times. Okay, in order for it to be mixing at the right temperature. Copper. All right. Basically, got some temper designations. So 6061 T1. Right. Starting to figure out some of this stuff is tempered versus strain hardened, as fabricated, or if it's been annealed. And so it goes back to that cold rolling. Some of the effects that we do on the finishing process make a big difference as well. So metallographic testing, this is basically, we're going to get back into this section here. We talk about macro versus micro. So macro is less than 10 power, and anything above that is considered micro, okay? Use magnifications greater than 10 power, usually 100 power or higher. So these are macrographs, right? So we're seeing large ones. You can actually see the whole weld here, right? But here's a micrograph or a microstructure. So those are actually the individual grain patterns within it as well. Oh, pretty crazy stuff, huh? All right, so I want you to be looking at these type of things as well. All right, let's look at our PowerPoint. I don't see anything else that's really given me endurance limit. I would think about a piston, right? So it's cyclical. Okay. Soundness, again, think of Weld, so it's freedom from discontinuities. Work yourself through this. It's going to help you out quite a bit, but I'm not going to sit here and read in front of it anymore. Doing a little different approach, seeing if this will help out or not as well. Okay? All right, have a good day.